Hello, BC Calc. If you just saw The Bachelor up there, my wife was watching it on my iPad last night. I was trying to remove it, couldn't figure out how. I'm incredibly embarrassed that it's even up there. Um, Before I get started on this, maybe number 3 or number 4, depending on how you count for our screencast this spring break, I want to answer Miss Yam's question. I was indeed old enough to be alive on that 1988 multiple choice question. I was about 6 weeks old. That should also give you a hint. And fun fact, both of us have birthdays coming up. So if you've made it this far in your screencasts, we expect that your birthday present to the two of us is that you will make it through all of these screencasts. So I'm here to talk about Maclaurin series. And namely, this is a calculus class, and we've been doing a lot of the series stuff, and it hasn't really tied in too much to the previous material. But today we're going to start talking about how to take the derivative and the integral of a Maclaurin series, and that will enable us to do a lot of interesting things, building on the first half of the year, such as maybe we want to know if one of these functions that can be described by a series has a local min or local max at a specific point, or maybe if it can satisfy a differential equation. I think you'll see both of those maybe later today on your homework from the screencast. So I wanted to start, we're in S1 on the last page, I believe. You started this problem, and a lot of those things, Miss Yam told us to ignore the last couple of problems on this page, but we're going to do them now. So find the first 3 terms of the Maclaurin series for f prime of x. Let's remind ourselves where we were. We had cosine x, and then we had to divide or decrease the power for each term there by 1 because of that x in the denominator. We memorized our Maclaurin series for cosine x, so this was a breeze so far. But now it gets a little tricky because they want us to find 3 terms of the Maclaurin series for the derivative of f. And we could, certainly take the derivative of f of x up there highlighted, but that's not necessarily where we want to go with this. Instead, we want to think about how we could take the derivative of this f of x. And there's sort of 2 ways. We could either take the derivative of the expanded form, which is in general definitely what you're going to want to do for almost all of these, or we could take the derivative of the general form and then expand out. So we'll do that 2 ways this one time. And then, we'll probably mostly do it the first way. So if we know f of x equals this polynomial, and it equals because we have that equality for cosine. If f of x equals this polynomial, well, then the first 3 terms of f prime of x have to be the derivative of these guys, right? So f prime of x, we know, has to sort of be the derivative of this thing. So the derivative of 1 over x is negative 1 over x squared. And then I'm going to have 1 over 2 factorial. And I'm going to have 3x squared over 4 factorial. And how you clean this up is really up to you. Some people might like this to say negative x to the negative second minus 1 over 2 plus 4 factorial. That is 24, so 1/8 x squared, perhaps, maybe something like this. I don't particularly care. Everything's sort of right. But this is it, right? We just simply take the derivative. It's as easy as you think it might be. And, we're going to be able to answer all kinds of questions now with that derivative. So let's now think about the general term here. If we were to take the derivative of this friend up here in green, right, we're going to take the derivative of that friend up there highlighted in green, and we need to be a little bit careful here, right? Because we need to think about an expression for f prime of x, right? F of x, I don't know what that pop-up is. f of x is the sum as n goes from 0 to infinity of this thing. So then f prime of x has to be the derivative of that, right? The derivative of that thing. And when we think about this, we need to be very careful about what variable we're taking the derivative with respect to, right? We're taking it with respect to x, taking the derivative with respect to x. So I'm going to actually throw all of this stuff that has n in front of it out at the beginning, right? And now I'm just going to take the derivative of x to the 2n minus 1, which of course is 2n minus 1 times x to the 2n minus 2. I don't know why I put parentheses around that, but there you have it. So we could then plug in 0, 1, and 2 for n and get these exact terms over here. I'm not going to. It's a lot more algebra. You're much more likely to make an error. I would just do it the first way when we can. So that's taking the derivative. It's fairly easy, right? Then you can sort of use that to answer all kinds of questions, right? You could answer all kinds of questions about anything we've done this year that involved a first derivative test or what have you. We can really do a lot there. Integration of these guys. This can be very, very, very similar, right? Very similar, and we can actually get some pretty interesting results for certain series when we integrate. And before we do that, I want us to recall this very simple rule here in my weird red and black pen that sort of changes color, right? And this is saying that the integral of a sum is the same as the sum of the integrals of the subpieces. And we're going to use that today, right? The integral of the sum is the same as the sum of the integrals, right? So if I'm taking the integral of f of x, right? If we're taking the integral of f of x, the indefinite integral of f of x, right? That would be the integral of all of these pieces. But really, we can break it up into this. Right? We can break it up into all of those guys, just applying that rule over there over and over and over and over. So this really isn't that bad, right? We're just going to take the integral of the first three terms, and then we're going to be done, right? So the integral of f of x here is going to be the natural log of x, right? That one's a little tricky, minus, what is this? Minus x squared over 4, perhaps? X squared over 4. Yes, and then plus x to the 4th times 4 factorial. And again, you could clean that up however you want. I don't feel the need to. I'm just going to leave it like that. But if that bothers you, that's tough. Okay, so that was good. That was good. And then I wanted to look at this friend who's not on any sheet that you have. But we're going to look at a definite integral now. And I'm going to want you guys to sort of play with it and sort of see what you guys can come up with first. So we have this sum here from 0 to infinity of n plus 2 over 2 to the n times x to the n plus 1. I guess there should probably be some dots here. Anyway, and I'm curious about what is this definite integral from 0 to 1 of f of x. Okay, and so what we didn't do up there is we didn't integrate the general term. We integrated all the individual terms. And now for this one, that's going to be a struggle, because if we were to integrate, this thing is infinite, and integrating that over and over and over and over again, I think you can see that the coefficient of the the out front is going to be getting very, very small, so that it might not matter as much. But we can't just completely ignore it, right? So integrating each piece is going to be very, very tricky because we're not asked just for the first three terms. So I'm going to want to integrate this thing. Okay, we're going to want to integrate this. And again, you know that our sum of my, the integral of my sum is going to be equal to the sum of my integrals. So let's talk about that. And if you would like, if you are bold, pause me and try to take this integral, right? Try to take this integral, just plugging this thing in. Try to see what you come up with here. Again, we are taking the integral with respect to x right here. Not with respect to n, with respect to x. So a lot of that's just constant noise. Okay, so pause me and try to take that integral and see what happens. Okay, hopefully you had a crack at it. This is going to actually just be a number, which is kind of a surprising result. Not involving x's or n's. Well, I guess it can involve x's. I guess it can involve n's. So of course we were going to get a number. That was kind of a silly comment by me. But if I wanted to integrate this, remember all that n stuff is just constants, right? We can sort of move it outside if we wanted to. So this thing is really we just have to integrate this piece right here. So what is this thing? It's the sum from n goes from 0 to infinity of n plus 2 over 2 to the n times what's the integral of x to the n plus 1? Well, it's x to the n plus 2 over n plus 2. And look at that. That's very nice of us. These friends go away very nicely. I don't know why one of those lines is so much thicker than the others. Anyway, and we're left with something that looks like this. And if we plug in 0 and 1 for x, I think you guys can all readily see that this thing is just going to be this. Because at the upper limit it's 1 and the lower bound it's 0. So we're just going to get that, right? And this should be, you guys should be saying, hey, that's a geometric series. Sometimes in my class's travels, we've had to write it like this just to prove to ourselves that it is indeed geometric, right? That 1 isn't throwing us off, but it certainly is, right? You could list the terms if you wanted to. And this thing, remember, this sum is just a over 1 minus r. Be very careful about where we're starting here, right? We're starting at 0. So my first term is indeed 1, and then my other terms are, my r is 1/2, right? So I'm going to be left with 2. So maybe a surprising result that this definite integral happens to be 2, but maybe you got that on your own, and maybe that was kind of exciting. Okay, I think, am I going to give you this for homework? We'll do one more thing and then we'll be done. So I think we'd seen this part A here. Part C is a real doozy. If you ever want to, if you get so excited after you do your homework tonight, and you want to try part C here, do it. And then, you can either look up the answer or you can check back. But we're going to do part B here together because it's kind of fun. So we found 1/3 as our R, our radius. In a previous screencast, I just want to note that I've rewritten this term. So I like patterns. I don't like simplifying that to 3x cubed. If that bothers you, too bad. So write the first 4 non-zero terms of the Maclaurin series for f prime, the derivative of f. Okay, so this is f of x. I've written out 4 terms, right? Obviously, there's a ... here. So my first derivative here, well, that's going to be kind of easy, right? It's just going to be 1 minus 3x plus 9x squared minus 27x cubed. Okay, those are my first 4 terms. We're done. Express f prime as a rational function when x is inside that radius of convergence. Now, this part is kind of crazy. How on earth can we express f prime as a rational function? We don't even know what f is, right? There's no f in this problem. We're just given the series for a function. So how on earth could we do it? Well, let's think about what we just did, right? We just found this beautiful geometric series in our travels, right? So let's look at these 4 terms and pause me and see if you can come up with what we have here, and see if you can come up with an expression for these terms here. Okay, let's see if any of you gave it. I gave a big hint here when I said geometric, right? All of these guys, there's a common ratio. R is negative 3x. Every term is negative 3x times the previous one. So what does that mean? That means that if we were to extend f prime out infinitely, right, and use the dots, right, that means that f prime of x is a geometric series. Which is kind of surprising. F prime of x is a geometric series. That deserves an exclamation point. Therefore, f prime of x, if we're looking for the sum, could be listed as a over 1 minus r. Again, because we're talking about 4x in that radius of convergence, right? So for the x is where this does converge, we can say it's a over 1 minus r. If it was just in general, we couldn't, right? Because if you look at these guys, if x is a certain size, it's clearly going to diverge, right? So anyway, if we're dealing with these guys of a certain size, well, my first term is, of course, 1, and my ratio is negative 3x. So it turns out that this is a rational function for f prime of x, which is kind of cool, right? We took a derivative and something that maybe does or maybe doesn't have a nice nice function for itself, f. It has this beautiful rational function for f prime. Okay, so maybe you found that exciting, maybe you didn't. Basically, the gist of this, right, is that we can just take derivatives and integrals either of the general term or of the expanded form and get exactly what we want. So I would like you to try these friends for homework. So from S2, let's do 2A through C. I don't think you're ready for D. And let's do 5B. You already did 5A. And then from S3, let's do problem 3. And I will have another screencast to go over those answers with you shortly.